All right, aloha and good morning. How's everyone doing? Nice weekend. Doesn't look like there's much more people here than Friday, so it is what it is. We only got today, this week, next week, and the week after is all we have left. So 3 more weeks and a final. Remember that your final exam gets replaced by your final exam score can replace your lowest exam. So make sure you pay attention to that. Okay. The exam 3 is going to be coming up probably at the end of this week, I hope. I'm going to be, what's it called? Passing it out in person, but I'll also be posting it on Canvas if you're not going to be here. I hope to have it on Friday. I still have to make it. So we have to see. We're gonna finish off this last. So we ended last class talking about buffering capacity. So I just wanted to go over that again. This last question. So buffering capacity is the ability for a buffer to continue to work. A buffer will work as long as you have both acid and its conjugate, or the weak base and its conjugate, in solution. So we would say that buffering capacity increases as we have more more of each thing, so the higher molarity or the total molarity of the buffer. Therefore, let's take a second to look at this question. If you have a 1 liter buffer with 0.1 molar HF and 0.05 molar NaF, which of these will destroy the thing? So take a second and look at this and tell me which one will destroy the buffer. Any thoughts? So we have 0.1 molar HF, 0.05 molar NaF. What do we have less of? So if we had 0.05 molar HCl, hold on 1 second, get my pen working. If we had 0.05 molar HCl, will it destroy the buffer? I mean, it'll basically get rid of all of the 0.0 molar NaF, right? So that one could be the one. What happens if we add 0.05 molar NaF? Will that destroy the buffer? That'll just make it a better buffer, right? So that one is definitely not the right answer. Adding 0.05 moles of NaOH, that 0.05 will neutralize 0.05 of the 0.1 molar. So would that destroy the buffer? No. So A would be the one that would destroy it. I mean, technically, the buffer would no longer be a buffer, but it would probably not have a super large pH change at this point. But that buffer is now has used up all of one of its things. Does that make sense? So having more of both things makes that buffer stronger in general. Okay. So that wraps up 16A. Let's jump into 16B. 16B is kind of like accumulation of all these things that we've been looking at. Okay, what that means is we are going to pretty much, this is titration and pH curves. So we're going to be doing a titration this week in lab. And in this, what we're going to do is we are going to it's just a straight acid-base titration, but instead of doing it to where we're still going to do it, I don't even know if we're going to add pH indicator because we're going to be taking the pH of that buffer the whole time. I know what's it called, doesn't work that good for this case, right? Like the pH meters we've been using, but we'll do the best that we can. But basically, I would say the majority of this take-home exam is going to be figuring out the pH at different points in a titration. So let's go ahead and learn how to do that. So this is the wrong one. Let's see, 16B. Oh, no. Okay, so now we're on titrations and pH curves. So do we remember a titration? An acid-base titration is a solution of unknown concentration is slowly added to a solution of known concentration. So in a titration, one thing is known, one thing is unknown, right? We add them together. When we hit that endpoint, We theoretically know how much of each we have. I mean, we know how much it took of the known thing. We can work backwards to figure out how much of that unknown must be in there, and then we can figure out the molarity of that unknown. So we have to think about moles. We have to think about molarity. But the problem with the titration is as we add in more of the titrant, right? So we start off with 25 mils of the base or in the acid in the Erlenmeyer flask, right? And then we start adding in titrant. That as we add it in, that increases the volume on the bottom. So that's going to be the one thing that's, I think, different than what we've done with titrations in the past. So as we said, you can use an indicator. That's what you did in 115A and Gen Chem A. You added stuff until it turned pink, right? Now what's going to happen is we are going to plot this. So I think we're going to do this in lab where you're going to put your thing in. You might add a few drop. You might add a mill or two, write down the pH, add a mill or two, write down the pH. So basically we're writing down the pH after each milliliter of NaOH added. Okay. What's going to happen is it's going to give us this shape. Anybody know what type of mathematical function this is? Who in here is math savvy? Got to be at least one math major, right? What's this called? Like an asymptote or something? Anybody ever heard that word? I don't remember it, but what is it? What do you mean when it's cubed? I don't know either. I mean, I don't know. It's just showing that for the pH, notice that when you add between, so look at this, so for the most part, the pH stays pretty constant. Does everybody see that? Then after only a very small addition, the pH jumps enormously, okay? And it goes from acidic down here up to basic over here. That inflection point of the thing is what the equivalence point of this buffer is. And you don't need to worry about these words that much, but all I'm showing you is what do you think is happening so in this case here, actually it's an acid and a base. The pH is not really changing much. So this is a strong acid and a strong base. The inflection point of the curve is the equivalence point of the titration. And prior to the equivalence point, the known solution in the flask is in excess. So the pH is closest to its pH. So when you have more acid in that flask, the pH will always be acidic, right? Once it starts to hit that middle, once it hits the equivalence point, for a very small second, it's going to stay basic, and then it's going to be very basic because now we're just continuing to add base to this solution. Everybody see that? So to calculate the pH of this, at the equivalence point, when you have a strong acid and a strong base, what's the definition of a strong acid, Ian? The definition of a strong acid. Remember? Low pH is definitely one of its things. Honey, what's the main thing a strong acid does? It fully dissociates. What is the thing that a strong base does? Mitch, what does a strong base do? If a strong acid fully dissociates, what does a strong base do? Any thoughts? What do you think, Nana? It also fully dissociates. So in general, whatever the molarity of that thing is, the strong acid or the strong base, that's the molarity of H plus or OH minus. If you don't know anything about these things, that's the main thing you should know, because if you have to find the pH of a strong acid or a strong base, that's the way to do it. And that will be important in these titrations, okay? If we have equal amounts of strong acid and strong base, Bailey, what do you think the pH of that's going to be when you add equal amounts of acid and base to each other? 7, right? So when we try and find the pH of a strong acid, strong base titration, we should get an equivalence point exactly equal to pH 7, okay? So finding the pH at different points in the strong acid, strong base is really just finding the stoichiometry of how much acid was added or how much base was added, which if it's equal, it's at pH 7. If there's more acid, you just have to find the pH, or you just have to find the concentration of how much acid is left. So remember we did the stoichiometry calculation in a buffer, right? Where we know the moles of buffer of acid, and then we add in moles of base, and then they neutralize and things like that. All of that's going to come into play here. So in general, we can like talk about this. That's just showing if you put the base in the Erlenmeyer and then titrate in acid, it'll look like this. That's when you add HCl. If you put acid in the bottom and you titrate in NaOH, it'll look like this. Okay? So let's calculate. So whenever we're trying to do this, I'll probably give you one of each of these on the take-home exam. Okay? And actually, I think I'm going to make the exam have to be submitted on Canvas. You will only get one try, so make sure you do it correctly. Like I said, I may or may not put the right answers in so that if people are submitting at different times, I don't want someone saying like, oh, actually, it's not gonna give you the right answer. So it'll just tell people when they get the wrong answer. But this is a take-home exam. You can use all of your notes. You can use all of the notes I give you. You cannot use the internet. You cannot talk to anyone. If I suspect you of cheating, I'll just give you a 0 and save myself the time of grading that exam. Okay? So don't try and cheat, okay? Like is it nice that you're able to use all your notes for this exam and have, it's not unlimited amount of time, but a lot more than the 50 minutes that I've been giving you? Everybody agree that that's pretty nice? So don't blow it, okay? Don't blow it for the future people who I might give a take-home exam to by cheating. So look at the notes. Everything that you need to know is in the PowerPoint slides that I've given you. Maybe this will get some people looking at the PowerPoint slides. You know, on Canvas, I can see who downloaded them. And right now we're at like 7 people out of this whole class who downloaded them. I'm just kidding. I can't see that. I can see who watches the videos and stuff, but I've never checked that because that's beyond the amount of time. But don't tell me you watch the videos when I can go look in your Canvas profile and see who's looked at things and stuff like that. Okay. So don't BS me. Like, I really don't care. You can lie to me all you want, but when you get caught up in a lie, it sucks. So don't cheat. Do it to the best of your ability and just understand the material. So let's say we're doing a titration with 25 mils of 0.1 molar hydrochloric acid. So in this case, we're going to put in this is a Erlenmeyer flask, okay? We're going to put 25 mils of 0.1 molar HCl in that flask. And then we're going to put a burette with sodium hydroxide with unknown molarity. Or actually, no, it's not unknown molarity. So in this titration, we're using known amounts of each, okay? So this one is like a little different than the unknowns that we're trying to find. Normally, we use an unknown. We can calculate what the pH by finding what the equivalence point is. In this one, we're just testing the pH at every point. So if we know the molarity of both, we're going to see how that stacks up in lab. In lab, we only have 3 weeks of lab, this week, next week, and one more. I think the last week is some like gnarly redox reaction titration. I'm considering dropping that lab and turning it into a final exam practice in lab worksheet. Okay. Anybody going to be crushed that we don't get to do a second titration in 3 weeks? And that titration is just confusing and crappy, and I'm not doing that. Oh, you want to do that, Emily? So since Emily, just kidding, Emily. So I'll talk to your lab professors about it, but I think, like that last week of lab, let's just get the lab done, that way in the last week we can start focusing, because it's not only going to be my finals, the only exam that you have, right? But that way I will make a review sheet to kind of give you an idea more so what to focus on for my final exam. The final is cumulative. There will still be some questions from earlier, but it's going to be much heavier in the chapter 17 and 18 material, okay? So we're going to wrap up chapter 16. by the end of this week. Then we'll have chapter 17 and chapter 18. We're only going to dabble in a little bit. It's cool. Electrochemistry. It's not that cool. No one ever actually calculates it. We'll talk about that. So in this case, we have 0.1 molar NaOH. So can we calculate exactly how many mils of NaOH it will take to neutralize all of this HCl in here? What do you think we should do in this case? Robert, how would we calculate it? So we want to find what's the equivalence point, right? So if we know how many mils of 0.1 molar HCl we have, can we calculate how many moles of HCl is in that little thing? And how do we do that?
Moles per liter.
So it's 0.1 moles per liter.
So we would just take the 25 milliliters, convert it to liters, and then multiply it by 0.1.
Very good. So we take this 25 milliliters, convert it into liters. If you don't know how to do that, we would go 25 mils, 1,000 milliliters equals 1 liter. That would give us the 0.025 liters we see there. We convert it to liters so that when we multiply by the molarity, we put liters on the bottom so it cancels. That tells us we have 0.0025 moles of HCl in that flask. Okay? Everybody good with that? So what we're going to do now, how many liters of NaOH will it take to neutralize that stuff, Jack? So if we have 0.025 moles of HCl, we can say for every 1 mole of HCl, it neutralizes 1 mole of NaOH. This is just stoichiometry from HCl plus NaOH reacts in a 1-to-1 ratio to give us water and NaCl. So that thing is from this 1-to-1 thing right here. Everybody comfortable with that? And now moles of HCl cancel. We're in moles of NaOH. So we're going to use the 0.100 molar. And remember, the 0.100 molar NaOH means 0.100 moles per liter of NaOH. But that also means 1 liter per 0.10 moles. So you see how I can use it either way? Why did I use this one and not this one over here? Any thoughts on this? Kobe? Why do I use this version with the mole on the bottom and not the one with the mole on top? Why did I use this one right here? It's to make this moles of NaOH that's on top cancel. Okay? So that's how we decide when we multiply or divide by it. I know students like to say like, oh, you can just convert from liters to moles by dividing or convert from moles to liters by multiplying or however you do it, right? I think I said that backwards. And since I said that backwards, I never try and memorize whether you multiply or divide. I just always write out my units so that they cancel. So this would tell us that we have 0.025 moles of NaOH. The molarity is 0.1, so we divide by it. That means that the equivalence point will be 0.025 liters, which if we were going to convert that into mils, would be 25 mils of NaOH. So anytime the concentrations are the same, doesn't it make sense that you would use the same volume of those two to calculate them? So in these practice problems, it's using the same volume. I'm probably on the test going to give you 2 different concentrations. So you'll follow these same steps. You just have to put in the different concentrations and things like that, okay? I show you how to do the work. Don't be super robots. All you have to do is be able to substitute in whatever you need to substitute in, okay? So that tells us what the equivalence point is. So for this, so what this question's asking, what is the question asking? We want to find the pH at different points in the titration. First of all, can we calculate the pH before any base was added? Do we know how to do that, Bryce? How do you find the pH? What would that be the pH of? Not times 0.100, right? Oh yeah, it is times 0.100. Why times 0.100? Since this is a strong acid, so before any base is added, does everybody see we're just calculating the pH of a strong acid solution? And as Bryce said, all you need to do is if the molarity of that is a monoprotic acid, which is the only ones I'm going to give you, I'm not going to give you any crazy ones, right? If it's a 0.1 molar HCl solution, that means at the beginning, before anything's added, that solution's 0.1 molar. Everybody comfortable with that? So now what happens is the pH, so let's put up here pH at 0 mils added. So that's what we're solving for. Since it's a 0.1 molar HCl solution, we just have to take the negative log of 0.1. The pH is 1.0. Everybody comfortable with that so far? Okay. So that's an easy one. The first step in the titration is always going to be pretty straightforward. The main one that I want you to do on the exam is going to be a weak acid and a strong base, which means you're going to have to find the pH of a weak acid solution. That would be like what we did in chapter 15, finding the pH of the different weak acids. You'd have to do an ice table and things like that, okay? So when I say like these problems are really all inclusive, all those things we learned in the last chapter and a half are redone here. So that's why this titration problem pretty much covers 75% of the test, okay? This is the easy titration problem, so you guys know. So let's find the pH after 5 mils of NaOH is added. And actually, I want to keep that thing over there. I want to leave that in the upper right. Okay, so after 5 mils of NaOH is added, right? What happens if I have, I calculated that I had an original concentration of HCl was the 0.025 moles. Where did we get that, Robert? When we were just finding the equivalence point, right?
Yeah.
So remember, to find the equivalence point, we wanted to figure out how many moles of HCl are in there. You always want to find out how many moles of HCl are in there to react, okay? So we have 0.025 moles in there. And now when we add 5 moles of NaOH, what we have to do is we have to see how many moles of NaOH we're adding. Everybody with me so far? So we're adding 5 mils of 0.1 molar NaOH. So to calculate that, 5 mils would be 1,000 milliliters per liter. In this case, they manually do it. They know that 5 mils is 0.005 liters. You can do it that way if you're comfortable doing that calculation in your head. As you go, you do this more and more, you see that it's pretty straightforward to go from mils to liters when you practice it a lot. It's easy to make mistakes when you're only doing it once or twice. So that's why I have you practice the homework so you can get used to doing it. This will give us liters of NaOH. Now we're going to use moles over liters or liters over moles in this case. What do we think? Riley, which one do we use? The one on the left or the one on the right? You think this one? What is my units right here? Okay, everybody see? We're in units of liters. If we use the right, moles will not cancel that liter. So we have to use this one over here, moles per liter. And that means we're going to put the 0.100. And that comes from the molarity of the NaOH that's added. So that tells us 5 divided by 1,000 is 0.05 times 0.1 gives us 0.0005 moles of NaOH added. Okay, so in that 5 mils of 0.1 molar NaOH that we added, there's 0.005 moles of NaOH. That's why over here, we did basically like a stoichiometry problem like we did with the buffer. We start off at 0.025 moles of H plus. Does everyone agree that if we add 0.0005 moles of NaOH, which is OH minus, we will subtract 0.0005 moles from the 0.0025. Everybody see that? So we have to be able to convert from molarity into moles or vice versa. That's going to be the important part of this. Okay? That gives us 0.002, and there's those extra zeros. You can leave them on there for sig figs. I'm going to just leave them off because they just make more work on here. 0.002 moles of H plus left over after the 0.0025 that was there originally gets reduced by 0.0005. 0.0025 minus 0.0005 leaves us with 0.002. That's where that's coming from. Everyone comfortable with that? So now, what did in the other one, in the buffer problem, we used stoichiometry and we said that H plus was converted into the conjugate acid, right? Since this is a strong acid, strong base, there is no conjugate base of it because it's a strong acid. So the Cl minus will not grab the H pluses or anything like that. So now we have 0.002 moles of H plus left over. But if we want to find the molarity of the solution, let me get rid of it. So erase some of this. If we want to find the molarity of the solution, what we have to do now is we have to take those 0.002 moles and we now have to divide it by the 25 milliliters that was originally in there. But did we add 5 more milliliters of base? Yes, we did. So we now have 30 milliliters total solution. So we have to do 30 mils, 1,000 mils per liter. That is 0.0. Oh, that's one too many. 0.030 liters of solution. Okay. So now to find the molarity, we take So the good thing about the strong acid, strong base is we're not doing any ice tables. We're not doing any Henderson-Hasselbalch because it's not a buffered system, right? Strong acid plus strong base just neutralize each other into water. And then their anions or cations that are counterions are all pH negative. So that's why all we have to do is find the molarity of how much H plus is left. 0.02 moles of H plus left over divided by 0.03 liters gives us a molarity. Someone punch that into your calculator. What did we get? That what we got? Let's think about this. If we started off with 0.1 molar HCl and we add a little bit of base, should the new concentration of H plus be less than the 0.1 that it started with? Yes, it should, right? Because we reacted some. The concentration should be less anyway, even if we just added water because it's slightly diluting it. So it should definitely be lower. And now how do we find the pH at this point? This is the H plus concentration. How do we find the pH of 0.0667 molar H plus? Emma? Very good. We just take the negative log of 0.0667, and that gives us a pH equals to 1.18. Does it make sense that the pH went from 1 to 1.18 when we added some base to it? Everybody agree with that? So you feel confident about that, okay? So I did this thing wrong. I wanted pH. This should be the pH over here, and this should be mils added. So with 0 mils added, the pH was 1. After 5 mils added, the pH went up to 1.18. Okay? So now let me erase all of this stuff. So that is how so do you see what we have to do? We have to use stoichiometry to find out how much of the H plus got negated from the added OH minus. And then what we have to do is we have to, I don't know if there's a bigger eraser. I guess not. Okay, let's just write it up. Rewrite this. So it started at 1.0, it went up to 1.18. Okay, so you could calculate this on your own. You can verify this on your own. When you add 10 mils, that would mean you're going to be adding 0.1, let's see. We started off with how much did we start off with? We start off with 0.0025 moles to start. Moles of H plus. When we added 5 mils, it was 0.0005 moles added. When we add 10 mils, it should be 0.0010 moles added. Okay. When you add 15 mils, it's 0.015. When you add 20 mils, it's 0.0020. You see how you keep adding a little bit more base? You keep subtracting a little bit more stoichiometry from the original H plus concentration. Does it make sense that the pH should continue to go up? Yes? Okay, what happens? So if you want to, a good practice thing would be doing these calculations on your own. Verify that you get those pHs. After 25 mils of NaOH is added, now what happens is we had 0.00025 moles of H plus originally. At equivalence point, we add 0.00025 moles of OH minus. If all of this H plus gets neutralized by all of this H minus, we make a bunch of water. We have a bunch of Na plus and Cl minus. What should the pH of this system be, Ricardo? If all 0.0025 moles of H plus gets neutralized by 0.0025 moles of OH minus, there's no more H plus, there's no more OH minus. The counter ions are pH neutral ions. What should the pH be? It's more than 6 and less than 8 and a whole number. Nana? 7. What does pH 7 mean? No more acid, no more base, nothing changes the pH. When you have, so the take home message is when you have a strong acid and a strong base with equal amounts, there will be no change. The pH is changing the whole time, right? The pH is going from acidic. When you're equal, they're now neutral, right? Everybody agree with that? So now what happens is that's how you find the pH there. What if we did 30 mils of NaOH? How would that change the problem? Somebody tell me. Any thoughts? Kayla? The solution now, so when we add 30 mils, at 25 mils, we added equal OH minus as we had H plus, because that was the equivalence point that we calculated at the beginning, right? So they were equal. Once we add 5 more mils of OH minus, the solution has to be basic, right? There's no H plus to calculate. We now can calculate, okay, so when we added, so we did 30 mils times 0.1 liters, that means we had 0.003 moles of OH minus. Everyone comfortable with that? So we add 0.0030 moles of OH minus. That's going to get rid of all of this. There's no more H plus, but we have 0.00, is it one more 5 or 0.0005? Let's see, 1, 2, 3 moles of OH minus in excess. Everybody see that? How do we find the molarity of this? What's our thoughts on this? Jackson? So what is the units for molarity? Moles over liters. So we have the moles of OH minus in excess. So what do we want to do to those moles? Divide it by the number of liters, right? So we want to divide it by the liters. How many total liters did we put in here? We had the original 25 of the acid plus the 30 mils of NaOH that we added from saying that we added excess. So that's 55 mils. We would convert that into mils per liter. And that's going to give us 0.005 moles divided by, let's change color. What is this? 55. So this is divided by 0.055 liters. That's going to give us, verify that on your own, 0.0005 divided by 0.055. Shout out the answer for me. How much? 0.00909 molar. This is the OH minus concentration. We can do the negative log of this to find the POH, which gives us, so what is the negative log of 0.00909? Huh? Did you get it? Shut it out. The negative log of 0.00909. 2.04. Would a pH of 2.04 make sense for excess base? Luckily, it's not the pH, that's the POH. So 14 minus 2.04 would give us 11.96 is the pH. Is that a basic pH? They went and solved for to get 11.96 by taking the OH minus concentration using KW, which is 1 times 10 to the negative 14th. So if you would rather do it this way, you can do it this way. I always find the POH and subtract it from 14 because it's 1 less times 10 to the negative that I have to, or a couple less times 10 to the negatives that I have to do. You can do it this way if you so choose. If you learn this on your own, you do it this way. And you think textbooks are very easy to read? Yes? No? You have to read a textbook first to see if they're hard or easy to read. And if you do, you'll realize they usually suck. Actually, you know what's weird? When I read a textbook now on something that I know, it makes a lot of sense. Everything is very difficult to understand the first time through, which is why I told you. Remember on Friday I said, look through these slides beforehand? Anybody do that? No? Well, good for everyone, okay? You can calculate the pH at all of these different excess points. So that's the easy one, okay? Should we jump in? So let's summarize what happens. The initial pH is simply the pH of the strong acid solution. And it's not being diluted at all. So you just find the molarity of the strong acid. That's the first pH. Once you start adding in amounts of OH minus, you have to calculate everything into moles. So you start off in molarity. You use the molarity to find moles of each thing. And then you subtract the moles. And then you have to divide by the new volume as the stuff got titrated in. So this is now a little bit more difficult. It's more steps than we've been doing, but it's not really anything different. With a strong acid and a strong base, the pH at the equivalence point will always be 7. Once we go beyond the equivalence point, you just have to find out how much OH minus is in excess and then divide it by the total volume to find the pH at all of those points, okay? So before the equivalence point, you just figure out how much H plus has not been reacted and then divide it by the total molarity and find the pH of those. So it's just finding the pHs or POHs by calculating everything into moles, okay? Is it difficult? Not at all. Is it difficult after learning it for the first time? Hell yes. So start practicing it, okay? We got 10 more minutes. Let's jump into the thing. If we switch from a base to an acid, you do the exact same thing, just in the reverse direction. Since this is a take-home test, should I do this? Maybe, maybe not. I probably will just use random letters. Like I theoretically could say like find using acetic acid, but I'm pretty sure nowadays you could type into AI what is the pH after adding 7 mils of 0.4 molar NaOH to a 0.3 molar Na or acetic acid solution, and it would give you the actual answer. I don't want that, so I'm going to put in fake names for the acid and base, so you have to use that stuff. You probably could, if you're good at AI, you could probably still do it. But you know what? Learn how to do it. It'll make your life easier, okay? Because even though I say that the exam is mostly, the final is mostly going to be on chapter 17 and 18, one of these, so forget the strong acid, one of these problems is definitely on the take home, and then I'll put another one on the final exam also. Okay? The final exam you have 2 hours for, so make sure you take this time to understand how to do these problems. Okay? Because there's 100% chance that this problem in this some type of form of this problem will be on the final exam. Okay? So if you need the kick in your pants to say, know this because I need to know it for 2 tests, then know it. And really, it's for 3 tests, right? It's for the third exam, it's for the final, and if that final's higher than exam 1 or 2, that's basically 3 exams. So if you get this stuff really well, if you've been loafing this whole semester, you can still get over 75% of the test scores back just by knowing how to do this really well. Okay? You ever been behind the 8 ball and you're like, damn, I really got to step up to like do this? That's how I always was in college. Like I would like, I mean, once in a while, I like had a 96% going into a final and I could like loaf on the final, but usually I'm like, damn, I'm at like a 91% or 88%. I need to like come up huge to get the A in the class. And that was like my motivation. Those classes where I only needed like a 60, I barely got that 60 because that's what I knew I needed. Okay. So if you need a jolt of, I can still do well in this, let's do it. Okay. So let's see what's different when we do a weak acid and a strong base. So we're not going to have time to do this whole problem, but the fundamentals are pretty much the same, okay? So now, titrating a weak acid with a strong base results in differences in the titration curve at the equivalence point and excess regions. So if we have a weak acid, let's just say it's exactly the same, 0.1 molar, and we had 25 mils of it. When we add 0.1 molar NaOH, how many mils of this would it take to reach the equivalence point? What do you think, Cade? You shouldn't have to do much calculations. It's 25 mils, okay? It's going to take 25 mils of this to reach the equivalence point. Now, does anybody find that weird that we're using a weak acid? Doesn't it not dissociate? Why would it take the same volume of base to neutralize it? Can anybody explain that to me? Any thoughts? Yeah, but this is a strong base that fully dissociates, and this is a weak acid that doesn't fully dissociate. Why? So remember, when we did this with a strong acid, it was the same 25 to 25. And now I'm saying the equivalence point will still be the same, even though that weak acid doesn't fully dissociate. Can anybody explain to me why that is? Any thoughts? So even though this thing's not fully dissociating, right? When that base is out there, if you're not dissociated by Le Chatelier's principle, when that base takes away your H plus that's in solution, what happens when you remove some of your thing? You're gonna move forward, right? So if if the product of HA is to barely make H plus and A minus, right? Remember, the whole point is this doesn't fully dissociate. But if the OH minus coming in takes away this H plus, if I remove from the products, what does that mean this HA is gonna do? Make more H plus. So it's gonna keep making more and more. So even though it's a weak acid, the total amount is gonna be the same. Now, at the equivalence point, what would the pH be, Ricardo? Got you. No, it is not 7, okay? Why is it not 7? but I'm glad you were ready for that. Bryce, why is it not 7? So at the equivalence point in this case, okay, what the heck did I just do? At the equivalence point of a strong acid, strong base, all of the OH minus neutralize all of the H plus. The reason it was pH 7 is because the strong acid left Cl minus in solution and the strong base left Na plus in solution. And what are both of those things? Non-pH changing, right? But if we have a weak acid, let's say it's HF, right? At equivalence point, all of the H plus is neutralized with all of the OH minus. Those are neutral. But now in solution, we have F minus and we have Na plus. So going back to salts, would this be an acidic salt or a basic salt? What do we think, Amanda? NaF. You remember what Na plus for you, Amanda? Yeah.
Sorry, I was watching the slide. Can you repeat the question again?
So if you have Na plus and F minus in solution, so this is the kind of question that will also be on the take home. I want to know, is this a acidic, neutral, or basic solution? What would you say? And you usually break it into parts. So between Na plus and F minus. So the Na plus is pH neutral. Everybody remember when something's pH neutral? When is it pH neutral? When it's from a strong acid, right? Groups 1 or 2. So that comes from the strong base, sorry. When it comes from a strong base, that means it's a pH neutral ion. Is F minus come from HF? Is that a strong base acid? Is HF a strong acid? It is not, right? So that means that it wants to grab H plus. So is F minus going to be acidic or basic, Bailey? It's going to grab some H plus off of water, liberating OH minus. So this is a slightly basic counterion, okay? So when we do this, at the equivalence point, it's different. So right away, at the equivalence point, because we're going to have F minus in there, it's going to have a pH slightly basic, okay? So we're going to continue on with this. So the initial pH is determined using so to find the initial pH, it would just be finding the pH of a weak acid. That's straight from chapter 15. That's straight using an ice table, right? So we'll just do an ice table. We're going to redo this stuff all again. So I'm going to go through it quickly right now. We're going to start it again on Wednesday, okay? So notice how we have to do an ice table to find using the Ka value of formic acid in this case, to find that the pH is acidic. So a weak acid solution should have an acidic pH, right? Remember, a strong acid at a pH of 1, a weak acid at the same concentration has a pH of 2.37. That makes sense, right? Because it's not dissociating as much. Now, in the excess region, we're going to now have to do a stoichiometry problem. And this is exactly like the stoichiometry problems that we do for buffers. So if we start off with we figure out how much acid we had in the beginning. After the addition of, in this case, 5 mils of NaOH, that means we added 0.05 moles of OH minus. This goes down by 0.05. But now, even though we had no conjugate base in there before, we're now making some conjugate base, which is CHO2 minus. This is the conjugate base of the weak acid. Okay? So now we have moles of these things. When we have a weak acid and its conjugate base, we could either do an ice table. What's the other thing we can do? Loit? What is this thing right here called? Sounds like Benderson-Hasselbalch. The Henderson-Hasselbalch equation, okay? So now, then the nice thing about that is this all in the same solution? Yes, it is, right? It's all in one flask. Even though we only have the moles of this, remember how I told you we didn't have to use molarities if the ratio, it's just a ratio? The nice thing about the Henderson-Hasselbalch is we don't have to take the time to do all of the calculations for the molarity of each thing. You could do it, but if you divide both of those things by 30 mils, doesn't have the same ratio if you don't divide them both by 30. So we'll redo this on Wednesday, and this is the meat and potatoes of the third exam and a very meaningful part of the final exam. So if you have friends who are not here, let them know this is a good day to come to class, all right? Sorry for leaving you a minute late. I'll let you out a minute early on Wednesday. Aloha.